Taking a look at our inclined plane worksheet that you guys have been working on since Wednesday. 3 questions that we want to go over here, questions 11, 13, and 14, starting with question number 11. The questions up on the board right now, we want to find the acceleration of the object in this situation, this 5 kilogram object. You know where to start, right? Everybody has a place to start. There's no excuse for not having a place to start with this. Draw a free body diagram. Okay, we know that we have a force of gravity acting down. What else we got acting here? What else, Logan? Normal force. Normal force acts perpendicular to the surface. Logan, tell me when to stop drawing the normal force. Okay, good. That normal force has to be drawn such that it is perpendicular to the surface and that it's also perpendicular to that red force right there. What do we call that red force? Zach? Yeah, I'm going to call it F parallel. Call it F parallel because it's parallel to the surface. If you draw that green normal force too long, then you're going to get F parallel that's not parallel to the surface. And that's a big deal because this angle up here, 30 degrees, F parallel, when I draw it this way, is opposite to that angle. If I draw it a different way, then it's not necessarily the opposite side, and I don't necessarily use the right trig function when I'm trying to find it. Let's get that value of F parallel right now. It's the opposite side, so we'll use sine 30 degrees is equal to opposite over the hypotenuse. F parallel ends up being equal to mg, 5 times 9.81 times sine 30 degrees. 5 times 9.81 times sine 30 gives me 24.525 newtons. All right. Now we got 2 forces acting here. Well, really we have more than 2, but we're going to include 2 here. F parallel plus F. We don't even know actually if that's friction or not, right? That 50 Newton force. In all likelihood it is, but it could be somebody pulling it up the hill with a force of 50 Newtons. It doesn't change anything. M is 5 kilograms. A is what we're looking for here, F parallel. I'm going to make negative 24.525, and I'm going to make F positive 15 Newtons. Do the math there. Negative 24 plus 15 gives me about negative 9. Divided by 5 gives me a negative 1.9 meters per second squared. Why am I not including F normal, the normal force here, and the force of gravity? Why do I not include that, Emily? Yeah, it is F parallel. I am including it already, right? It's F parallel already accounts for the normal force and the force of gravity. If they don't cancel, and they don't cancel, the Fn and Fg do not cancel here, then I have to account for them. But I am accounting for them. As we said this a million times, right? Fn and Fg combine to give me F parallel. So by including F parallel, I'm including Fn and Fg already. All right, next question was number 13. In this one, we were asked to find the force of friction. And number 13, given the acceleration. I should write that down. The acceleration was 1.5 meters per second squared up the hill. So what do we got here? Well, we got a force of gravity acting down. We got a normal force acting perpendicular. As Logan said in the last question, we're going to stop drawing it there such that it's drawn 90 degrees to the surface and that it's also drawn 90 degrees to F parallel. This is 30 degrees. Let's draw F parallel right here. And let's find the value of F parallel. We'll say sine 30 degrees is equal to opposite, that's F parallel, over the hypotenuse, which is force of gravity. So what do we got here? 10 times 9.81 times sine 30. I think that one works out to be 49.05. All right? 49.05 newtons. All right, what are we looking for here? Friction. Which way is friction going to act? We didn't know. Actually, we did know. We should have known right off the top which way friction was going to act. It's going to act with F parallel, right, Nick? Why? Okay, force applied is greater than F parallel, yeah. But even before I calculated F parallel there, I should have really known that the force of friction was going to be acting this way. How? Let's say I didn't know what F parallel was. How would I know that friction is still going to act to the left there? Alex? Yeah, good. The acceleration is positive. It's up the hill. So if it's accelerating up the hill, then friction has to oppose that motion, going to be down the hill. I got a value for F parallel that was smaller than the applied force here. I never even thought of that at the time, but I should have predicted that it would have been smaller because it's accelerating up the hill. All right, let's do the whole net force equals the sum of the forces thing now. There's three forces, F parallel plus FF plus FA. There's actually a couple more forces, but I've already included them, right, with F parallel, as Emily said in the last question. When we have Fn and F and Mg, those are important, but we've already included those with F parallel. F net is M times A, 10 times 1.5. This time I have the value of the acceleration. Usually I don't. F parallel, I'm going to say it's negative 49.05. FF, I know that that's a negative value, but I'm not going to write it in as negative right now. I always wait till I plug in numbers to plug in negative or positive. If I'm solving for this variable, then I'll just let the equation tell me whether it should be negative or positive. FA is 80. 49, negative 49 plus 80 gives me about, what, 30.95. 15 on the left side, subtract 30.95 gives me a force of friction of negative 16 newtons. We predicted that it should be negative down the hill, and sure enough, it was down the hill. Two different people gave me two different rationales for that, right? One person said FA is bigger than F parallel, so therefore the friction has to be down the hill. Good. One other person said the acceleration is up the hill, friction has to be down the hill. Good. Both are correct. And one more question we had was number 14. Had a pulley here and an inclined plane here. We gotta, I guess in a sense, compartmentalize this question. Okay, turn it into a couple smaller questions. We know how to solve a pulley problem. We know how to solve an inclined plane problem. Let's solve this problem as two different problems, a pulley problem and an inclined plane problem. Let's deal with the inclined plane first. Let's say that there's a force of gravity acting down on it. We call it M times G. And we have a normal force acting perpendicular. Okay, as Logan said early on in this class, it's going to be drawn perpendicular here, and we stop drawing it about where we did so that this F parallel is 90 degrees to the normal force. Let's draw F parallel in there. You know what? Let's get the value of F parallel. You may not know where to go with the rest of this question, but everybody, again, knows where to start this. Everybody can find F parallel. So let's do that. Say sine 30 degrees is equal to opposite over hypotenuse. So we get F parallel is equal to 5 times 9.81 times sine 30 degrees. And that gives us, I think that was 24.525, was it? From that other question? All right. We just treated this now the same as we treated question 11 and 13. What do you suggest I do now? I got a 3-word answer that I'm hoping to hear here. Straighten it out. Straighten it out. So let's do that. Let's straighten it out here. Let's put a 5 kilogram object right here with a F parallel acting to the left of 24.525 newtons. And then let's put a 5 kilogram object over here with a force of gravity acting on it. We'll call it Fg of what? Mass times gravity, right? 5 times 9.81. Good? Why do I not use, listen, I use the force of gravity for this guy. Why am I not using the force of gravity for this guy? Sorry? Yeah, I am. I am using the force of gravity. Okay, if it doesn't cancel, I have to use it. I'm using it, but I'm using it in a little more subtle of a way, right? I'm using the force of gravity acting on the first 5 kilogram object in conjunction with the normal force, which combine to give me F parallel. So let's solve this the way we know to solve it now. Let's say F net is equal to F parallel plus Fg. Let's say, what mass do we use there, 5 or 10? 5? It would be the net, yeah, for the net force here. 10, right. Good. 10 times A equals negative 24.525 plus positive 49.05. Combine those, divide by 10, and we get 2.5 meters per second squared. How could I have made this question, how could I have added a little bit to this question without actually changing the picture at all? What else could I have asked in addition to what I already asked here? Yep. Maybe a force of friction, but that would change the whole complexion of the question, right? But yes, I could have done that. What if I had asked you to find the tension in the rope between the two? I didn't, but what if I had have asked you to do that? What would we do? How would what I do on the board change? Would I do anything different than I have on the board right now? Nothing different, just more. I would solve for the acceleration, right? Just as I just did, exactly the way I just did. And then what would I do after that? After I found the acceleration, if I want to find the tension, I would pick an object. Okay, probably would make sense in this case to pick the second 5 kilogram object right here, right? I think that one's a little bit easier to deal with because we don't have this crazy diagram that we have over here. All right, good. Finally, we have one more question we want to look at today, which is the question. Okay, here we go with this one. So here's the situation. We have this 500 kilogram object on an incline with a 80 kilogram elevator and a 50 kilogram person inside the elevator throwing a ball. The system is released. It's allowed to be released for 4 seconds. We don't know whether it actually moves upward or the guy just throws it from ground level here at 30 degrees. I guess we got to figure out whether it moves first or not, right? Where should we start? Everybody's got a place to start on this. Okay, I didn't say that you had to do this for homework, but if you did, if you tried it, it was optional, but if you tried it, everybody would have had a place to start. What's something that everybody, every single person in this class can do for this question? F parallel. Yeah, let's get F parallel. So let's do that right now. Let's say there's a force of gravity acting down on the 500 kilogram mass, and there's a normal force acting perpendicular. Let's get F parallel. Okay, let's get F parallel up here. Let's say sine 30 degrees is equal to F parallel. Actually, let's use red for that to keep the color coding. Let's say sine 30 degrees is equal to F parallel over M times G. Opposite of hypotenuse. So we're going to say F parallel is equal to 500 times 9.81 times sine 30. I get a value for F parallel of 2,452.5 newtons. Now, while we're finding F parallel, we might as well find the normal force as well, right? Odds are in a question this complicated, we're going to need the normal force. And you know what? If I don't need the normal force and I calculate it, oh well, I've just done something I didn't need to do, but it's not the end of the world. Okay, I'm pretty sure I'm going to need it. So let's get that now. Cosine 30 degrees is equal to Fn, the normal force, the adjacent side of the triangle over the hypotenuse. So we're going to say Fn is equal to mg cosine 30, which ends up being equal to 4247.8546 newtons. Okay, what else? There's something else here that I think pretty sure that everybody can do as well. What do we get the force of gravity acting on this thing over here? There is a force of gravity acting down on the elevator and the guy inside the elevator, and that force of gravity will be equal to 130 kilograms times 9.81, right? 80 plus 50, the mass of the elevator plus the mass of the person, times 9.81 meters per second squared. And when I do that, I get 1275.3 newtons. Got it? How do I know if it moves or not? Sorry? Yeah, 500 is heavier than the 130, but that doesn't tell us necessarily that it moves. We have an F parallel down the hill here of 2452.5 newtons. We have a force of gravity acting the opposite way of 1275, but we also have friction, right? Taylor? Okay, F parallel is bigger than the force of gravity, so if it's going to move to the left, which we would have predicted if it was going to move, but we still don't know if it moves or not. We have to account for friction and see if it will overcome static friction. Let's get the maximum force of static friction right now. Let's say SF max is equal to mu times the normal force. And mu is what? Static is 0.20. The normal force is 4247.8. Maximum force of static friction gives me 849.571. So here's the deal. It does move. It does move because we have force of gravity acting down at 1275. We have the maximum force of static friction acting this way of 849. When we combine 1275 and 849, it gives us around, I don't know, 2100 or so. We have a maximum force of 2100 pushing to the right due to friction and gravity, but we have 2400 newtons pulling down the hill, so that overcomes maximum static friction, right? Make sense? It moves. I was hoping it didn't move, because if it didn't move, then this would just be a projectile motion question, right? If it didn't move, we just analyze the motion of this thing. But since it moves, we got to deal with it. Okay. Let's straighten this out. If we straighten it out, we have pretend it's horizontal here. We have a 500 kilogram object right here. We have a 130 kilogram object right here. That's the mass of the person and the elevator. We have F parallel that was to the left of 2452.5 newtons. We have FG over here, which was 1275.3 newtons. And we have not the force of static friction, but the force of kinetic friction over here. Because it moved, right? How do we find the force of kinetic friction? Mu times the normal force. But it's a different mu this time, right? This time mu is a coefficient of kinetic friction, which is 0.10 times the normal force of 4247.8, giving me a value of 424.78546. So we've got this force of friction to the right, this force of gravity to the right, and we have F parallel to the left. What do you do with this? Yeah, listen, you're trying to find how far the ball goes. Like, why would we combine these forces? Because we can. We don't know exactly how we're going to find the motion of this ball. Don't worry about that right now. Do what you can. I'm going to combine these, saying F net is equal to the sum of the forces because I can. F parallel plus FKF, force of kinetic friction, plus the force of gravity. The net force is based on a mass of 630 kilograms. That's 500 plus 130 times A is equal to negative 2452.5 plus positive, this is friction, it's to the right, plus that force of gravity acting on the 130, which is 1,275.3 newtons. When we combine those and get the acceleration, I end up getting a value of negative 1.194309 meters per second squared. So that's stuff else it's accelerating at. Is anybody that had an answer got this acceleration, 1.19? Okay, 2 of you got 1.19 meters per second squared. Good. We're on the right track, hey guys. Problem is you guys don't agree on what your final answer is, right? What'd you get? 66? Sorry? 35? So you've done something differently somewhere down the road. All right, we got the acceleration. What do you want to do with that? Hey, I just finished one page of my solution. Only one page left. If I'm releasing this ball in this elevator after 4 seconds, then I want to know where I'm releasing it from. Where does it get released from? At what height is it released from? So I know that it's accelerating at 1.19 meters per second squared for 4 seconds. Let's find out how high it goes, how high the elevator is after 4 seconds. So let's say D is equal to VIT plus 1/2 AT squared. VI is 0 because this elevator starts at rest. 1/2 of, I'm going to say positive 1.194309. How come positive? Yeah, yeah. In this picture, it's going to the left, right? But the elevator is accelerating upwards, so I'm going to make it positive all of a sudden. Times the time of 4 seconds. Don't forget to square that. We get 9.55447 meters. So the height that the ball is released from is 9.55447 meters. It's that high off the ground when it's thrown. All right. Here's the tricky thing, and here's the thing where I'm pretty confident that a number of you would have made a mistake. Okay. Lots of you at this point will say, okay, look, this is great. He's throwing the ball from a height of 9.55447 meters. He's throwing it at a speed of, what was it, 20 meters per second? At an angle of 30 degrees? It's just a projectile motion problem now, right? Not quite. Not quite. Because the thing is, he's throwing it at 20 meters per second at an angle of 30 degrees, but the elevator is moving. If you're driving in a car at 100 kilometers per hour and you throw a ball out the window at 50 kilometers per hour in the same direction, how fast is the ball moving? 150. So he throws it at 20, but he's already moving upwards, right? So we have to include the motion of the elevator upwards along with how fast he throws the ball, because that gives it kind of an extra push, an extra initial velocity, like the 100 kilometers per hour the car was. So here's what I want to do. I want to find out how fast the elevator is moving when the ball was released. I'm going to say VF squared equals VI squared plus 2AD. VF is equal, VI is 0, so VF is equal to the square root of 2A times delta D, which is square root of 2 times 1.194309, the acceleration we already calculated, times the displacement that we just found. VF gives me 4.77723 meters. So this is how fast the elevator is moving when the ball was released at a height of 9.55 meters above the ground. Now let's draw a little picture. Here's the ball being released from a height of 9.5544. Actually, let's do something else first. Here's the ball being released at 20 meters per second at an angle of 30 degrees. Let's get the x components and the y components of this. Cosine 30 degrees is equal to adjacent over hypotenuse. The x component of the initial velocity ends up being 20 cos 30, or 17.3205 meters per second. And the y component ends up being sine but this is just the velocity due to me throwing it, right? This is not the velocity due to the elevator moving. So what I got to do for this, for the y component, is add 4.77723 meters per second. The y component becomes 14.77723 meters per second. You guys see what I've done there? That's a tricky step right there. Okay? The ball was thrown vertically at 10 meters per second, but the elevator was moving at 4.7 meters per second when I threw it at 10. So how fast is the ball moving vertically when it's released? 14. All right. Now it's just a straight projectile motion question. Now I'm going to redraw that again. My height is, 9.55447 meters. This is where it's released from. It's released with an initial x velocity, let's say, of, 17.3205. Okay, this value right here. And an initial y velocity of 14.77723. Oh, I'm so close. I'm so close to being there. We still have a little bit of a problem with some math here, but let's break it up into x components and y components. V equals d over t. Wouldn't this be a great final exam question? V is equal to delta d over delta t for the x component, and since it's projectile motion, we say d is equal to vit plus 1/2 at squared for the y component. The horizontal velocity was 17.3205. We don't know what t is. The vertical displacement, negative 9.55447, because it ends up 9.55 meters below where it started. VI for the y component, 14.77723. Well, let's rearrange this a little bit, simplify it a little bit. 0 is equal to negative 4.905 t squared plus 14.77723 t plus 9.55447. The reason that I rearranged it to take that order is because this allows me to find t using quadratic equation. How many people have seen the quadratic equation in math class? Negative b plus or minus b squared minus 4ac. If you haven't, don't worry about it. If you have, you say negative b plus or minus b squared of b squared minus 4ac all over 2a. This would be the value of a, negative 4.9. This would be the value of b, 14.77. And this would be the value of c. You'd use that quadratic equation to find t. And of course, if you've done that before in math class, you know there's two values. The first one is negative 0.54718 seconds, and the second one is 3.55987 seconds. It's not negative. What would the significance of that negative time end up being? Just out of curiosity, if you look at this picture, The 3.559 seconds is the time that it takes the ball to go from here to here. What would the negative 0.54 seconds correspond to? It's a non-existent time, right? It's an imaginary time. It's negative. It would correspond to this time right here, right? If it was going backwards from that point back to the ground. Make sense? So even though it's not a real time, it does have a significance. It's not just a random value for t. All right, now we can plug this back into here. And delta D ends up being equal to, Bruce, what did you get, 66? You were so close. 62 meters. Bruce, what did you do wrong? That's the thing that I predicted a lot of people would do. You got 3.8 for time? Okay. Okay. So you got 3.8 because you didn't include that 4 meters per second for the elevator speed. Yeah. What else? A number of the rest of you got answers here. Do you want to point out? You want to volunteer what you got wrong? Okay. The projectile motion part. That's all you did. Okay. The motion of the elevator. Okay. So you would have been okay, not so bad if static friction hadn't have been overcome. But as soon as it started moving, you were pretty much hooped. Anybody else? Nobody else wants to volunteer what they did wrong? At least you did it. Like those of you who got something wrong, that's okay. At least you did it.